this video, we are going to do a brief 6-minute summary of our second week's worth of content, which was covering log likelihood functions and gradient ascent. So let's start out with the likelihood function and how that leads to our log likelihood function. One of the things we did in our second week was review some concepts from probability, and the most time that was spent in that review was on covering the concept of independent events. And these are events that don't influence the likelihood of other events happening. We are going to make the assumption throughout all of our work that anytime we're talking about classifying multiple reviews, we're going to assume that those reviews are independent of one another, meaning that one person giving a positive or negative review does not influence the likelihood of another person doing so. The people involved are making their own decisions. So that's the assumption we'll be making throughout. And in that situation, we can define something that we call the likelihood function. So if we have a corpus of reviews that we're denoting by capital X, we're going to denote the likelihood function to be theoretically the product of the probabilities that the model we're looking at classifies a review correctly. Now, in order to do that, we need to split our reviews into positive reviews and negative reviews. So I've denoted those sets by P and N. We're going to use S of X, S of little x, to denote our scoring function. And our likelihood function then really just became the product of the probability that a review is classified correctly. So when we're dealing with a positive review, the probability that that review is correct is just given by the sigmoid function applied to the score of that particular review. However, things got a little more complicated when we were looking at our negative reviews. When we plug that review into our scoring function and then look at the sigmoid of that scoring function, that's the probability that the review is a positive review. The probability that we've classified it correctly as a negative review will be the complement of that within our space. So we split our reviews into positive and negative reviews, and then multiply all the probabilities together to come up with our likelihood function. And for me, this is the function that makes sense. However, this is not computationally the easiest function to work with, mostly because taking the derivative of products of things is difficult, while taking the derivative of sums of things is much easier. So the function we ultimately work with is called the log likelihood function, and all it is the logarithm of the likelihood function. But logarithms take products to sums, so we can alternatively write the log likelihood function of the corpus of documents in the manner we have listed in the bottom here. Now, if you take what's written on the previous page and you do take derivatives, despite the fact that derivatives behave nicely with respect to sums, you still get a very elaborate system of equations of partial derivatives that need to be set equal to 0 to find the critical points of our log likelihood function. However, if you were to write things down and very precisely mathematically try to solve this system of equations, that isn't actually possible. And so solving things exactly and theoretically on pencil and paper isn't going to work, and yet it's still important for us to find the maximum of this log likelihood function. And so in order to do that, we're going to implement an algorithm that we call gradient ascent. So the last thing I'd like to do in this video is walk through some code that would give us the gradient ascent algorithm and talk about what the purpose of these lines of code are. So we defined our gradient ascent function. It's going to need some parameters passed into it. One thing it's going to need is the gradient. The gradient is the collection of partial derivatives of a function. We're going to need a starting position, and we're envisioning this as a random guess as to the starting parameters that we're looking for, and we're going to modify that starting position according to the gradient. We need a list of variables. That's just, computationally for Python's sake, and we need a step size for how large of a step we're going to take in the direction that's given to us by the gradient, and we need an error measure to know when we've accomplished good enough that we're practically at the critical point of this function. Now, some of the mechanics of this program that we have here are just to avoid computational issues. So one of the things we've defined is a counter, which is really just there as a fail-safe so that we don't get stuck in an infinite while loop. So that's all that counter is doing. Converged is we're going to have a Boolean variable that tells us if we've converged or not. We want to assume at the start that we have not converged and then update that should we find that the magnitude of our gradient vector is less than our acceptable error. And we're going to define something which is our current coordinates, which is where we are as we're walking across this function, searching for the maximum of it. And in the beginning, that should just be whatever our starting position is. Then as long as we have not converged, and then we also have this little fail-safe so that we haven't overstepped our bounds, we're going to do a couple of things. The first thing we're going to do is a computational issue. We're going to create a list of substitutions to make. For each variable that we have, I need to know what to substitute in for that variable. And so that's what we have going on in this list right here. In step 9, we're going to then take our gradient function, and for each partial derivative, we're going to evaluate each partial derivative at the substitutions that we needed to make in step 8. We then compute the collection of corrections that we need to make. So we now know how to modify each coordinate of our current position. We want to take a step in that direction, but we don't want to take too large of a step. So whatever direction we should have gone, let's multiply that by the step size that was passed to us that we find acceptable. And then that's it. Let's update our coordinates. Let's compute what the new coordinates are. It's wherever we were plus whatever modification we want to make. And let's update the system. And then the stopping mechanism is if we take a look at the size of that partial derivative, the magnitude of the partial derivatives at this particular point, and they happen to be less than the error that we found acceptable, we'll say that we have converged, and we'll spit back the coordinates of that maximum.